We'll start now with the fourth session on this set of seminars, and this session is about thermal storage and hybridization. First, I will start having a short review, or presenting a short review of the CSP markets, of the concentrated solar thermal power markets, to understand why these topics, thermal storage and hybridization, are so important. These markets are mainly the first of them is the utility or centralized market. It's characterized mainly by the fact that the generators are centralized installations with normally a high capacity, over 10 megawatts. But that is not really relevant, but normally the capacity of these plants is over 10 megawatts. And we can classify these generators in three categories. The baseload generators, like nuclear and coal, which normally have to be generating the whole time. The dispatchable generators, like gas plants, for example, combined cycle plants, and CSP, here where CSP wants to be, that can be connected or disconnected from the grid at the request of the operator, of the grid operator, and the intermittent generators, like most of renewables, wind, photovoltaics, that depends on the resource, and they cannot be normally. These types of generators cannot be controlled by the operator. Well, of course, for this market, for the utility market, the key feature of CSP is dispatchability. Dispatchability is defined as the ability to dispatch power, and dispatchable generation refers to sources that can be dispatched at the request of the operator. As it's written there, these generators can be turned on or off upon demand. This characteristic of CSP to be dispatchable is the characteristic that makes it different from other renewable sources, like I mentioned, wind or photovoltaics, other renewable technologies. Other interesting markets too for CSP are distributed generation, where the capacity is normally lower, in the range of 3 kilowatts to 10 megawatts. But the main and most important characteristic is that the distributed generators are normally close to the consumer. Therefore, it allows for better use of the resources, because, for example, many installations can take advantage of the fact that energy is consumed both as heat and electricity, and therefore cogeneration installations are easier to implement in this market. Other advantages of this distributed generation market are that transmission losses and investment are normally reduced. Of course, there are also some difficulties for the deployment of these distributed generation resources, mainly that the network, the control of the network becomes more complicated, and it will be necessary more development of grid control concepts to take full advantage of this concept. But it's a growing market with tremendous potential. Finally, there are standalone applications, for example, electricity supply or energy supply to a village, to an isolated village, that could be also covered by CSP installations. These two markets, the key issues are modularity, availability, and reliability. In these two slides, we have seen pictures of, for example, the Andasol plants in Spain, 50 megawatts each, which are centralized utility installations, centralized installations, or PS20, also in Spain. And these two, this is a picture from the Maricopa solar plant with parabolic dishes in Arizona, in the United States, and this is the Saguaro plant, also in the United States, which is a parabolic Trough plant of 1 megawatt power, an organic Rankine cycle. So, in principle, all of the technologies that we have been describing in the previous seminars are appropriate for any of these applications. Of course, depends on the demand of electricity from the different consumers. In any case, CSP can cover these requirements from the different markets with the help of two unique features, like are thermal storage and hybridization. These are unique in the renewable energy world, because this thermal energy storage is only possible in principle with CSP, and hybridization. Of course, there can be different types of hybridization, but hybridization of CSP plants with conventional or renewable fuels is very easy, it's almost natural, say. What is thermal energy storage? Well, it's just storing the thermal energy produced by a solar field in in a storage medium, like could be molten salts or concrete or ceramic pieces of different materials, and and the storage of this thermal energy permits to decouple the power generation from the availability of the solar resource at a given time. Hybridization is just the ability to combine or to hybridize with an alternative energy source that can be a fossil fuel, like natural gas, for example, or a fuel derived from biomass, like biogas or just biomass. And this, the use of these two features permit CSP to be dispatchable, to be stable, to provide a stable generation and a reliable generation. Okay. We will start first with energy storage, although as we will see later, both of this thermal storage and hybridization can be combined in a solar thermal power plant. We will start first by describing a little bit thermal energy storage. Thermal energy storage increases the operational stability. Why? Because it provides the ability to operate smoothly during transients, reducing intermittence, increasing the plant utilization and capacity factor, because we can operate for more hours, we can avoid starts and stops, and also provides some peak shaving ability, because we can decouple generation from electricity generation from thermal energy generation. Thermal energy generation takes place during sun hours. Energy can be stored and used later whenever necessary, for example, during peak consumption times. And energy storage can reduce generation cost as long as storage is cheaper than increasing rated power. For example, the case in Spain, where we have a a plant, a solar thermal power plant. It's the Gema Solar power plant. Talk about it later, which is just 70 megawatts in rated power, but it provides storage for 15 hours, for 15 equivalent hours. So the generation of this plant with only 17 megawatts rated power is similar to the generation of a 50 megawatt plant during the year. We will see here how this thermal energy storage can be used. This is, for example, the profile of the electricity demand in Spain, the Spanish market. We can see two peaks. One that it's the morning peak, and the other one is during the afternoon. With solar generation, which is during, for example, clear day, in this case, the generation peak covers roughly the morning peak of the electricity demand. This would be without energy storage or without hybridization. If we have a thermal storage, we have the capacity to operate at more or less constant power during the whole day, for example, or we could even, it's not represented here, but we could even stop generation, say at this time, what I'm marking here, store the thermal energy generated by the solar field during these hours, and then generate again to cover the afternoon peak or the evening peak. Okay. So this is one of the interesting features of solar thermal power plants with thermal energy storage. Thermal energy storage is just consists in storing a fraction of the thermal energy produced the solar field during sun hours, and this energy is stored in storage medium that increases its internal energy. There are two main ways of storing this thermal energy. One is a sensible heat, where the increase in thermal energy is reflected in an increase in the storage medium temperature, mainly, and latent heat, where there is a phase change and a significant part of the energy, of the thermal energy, is stored as phase change enthalpy. There are also other possibilities. It's not strictly thermal energy storage, but it's related with that. It's a thermochemical energy storage, which it's a very promising concept that at the moment has only been developed at small scale. But in the future, I'm sure that it will have a very relevant role in the CSP market. Well, we can divide we can classify thermal energy storage systems attending to different criteria. But for example, I've included here two of them. One of them is by utilization. We can have short-term thermal energy storage, which it's mainly conceived to provide operational stability. That is to permit stable, smooth operation during short transients of solar irradiance. For example, cloud passages, short time cloud passages. This type of storage is normally provided either by a specific system, like in the case of PS10 and PS20 that we will comment in a few minutes, or even by the thermal inertia of the solar field. This is the case, for example, in the Nevada Solar One parabolic trough plant, which doesn't have thermal energy storage system, but has some thermal inertia associated with the solar field that provides some operational stability during transients. Then we have the medium-term thermal energy storage, which is oriented to increase the capacity factor and to shift the electrical generation hours from certain times in the day to other times, where for different reasons can be more convenient, because of the price of the electricity or just because the requirements of the grid operator. We can also classify the thermal energy storage systems by type. There are two main concepts: the direct thermal storage, where the same medium, the same substance, is used as a working fluid in the solar field and in the thermal energy storage. Therefore, it does not require heat exchangers. And indirect thermal energy storage, where the heat transfer fluid at the solar field is different from the thermal energy storage medium. In this case, of course, we have to use a heat exchanger to transfer the thermal energy from the heat transfer fluid of the solar field to the storage medium. There are also other possible classifications, for example, by technology, with one tank using the thermocline effect, or two tanks, a cold tank and a hot tank, or other different possible criteria for classification of thermal energy storage. But well, I think these two are quite useful. We are talking about thermal energy storage, and the main of course, very important factor is the substance that we can use for to store the thermal energy. There are certain requirements for these substances. First of all, these substances should have high energy density per unit mass or per unit volume, good heat conductivity that affects the charge and discharge processes mainly. It's desirable also to have a good heat transfer between the heat transfer fluid of the solar field and the storage medium. Of course, the storage medium should be mechanically and chemically stable, and there should be chemical compatibility between the heat transfer fluid of the solar field and the storage medium. Normally, the heat transfer between these two fluids takes place at a heat exchanger, and well, we must be sure that there are no type of problems in these heat exchangers in the case of a leak or any other problem or any other incidents. Okay. It's important to ensure safety in all cases. These materials should permit reversible charging and discharging cycles, a large number of these charging and discharging cycles without any degradation or with minimum degradation. Thermal storage should have low thermal losses, and it should be easy to control. These are different requirements for thermal energy storage materials and equipment. In the following table, I have I have taken them from a report from Pilkington Solar. It's 10 years old, this report, but it's interesting just to see the different storage medium that have been considered. There have not been many changes since then. For example, we can see here that we have that there have been experiences with solid media, with liquid media, and with phase change media. We can see here the temperatures, cold and hot temperatures, the density, the average heat conductivity, average heat capacity, volume specific heat capacity, and media cost per kilogram and per kilowatt hour thermal. For these all materials. Of course, these figures are rather outdated, but of course, but they provide a good indication. Within the solid media, we can see here different materials like sand rock mineral oil, sand and rock with mineral oil. We will talk about this is a dual medium, or reinforced concrete, or sodium chloride, iron, steel, bricks, etc. In liquid media, different types of oils and salts mainly, and also liquid sodium, which was used at the SSPS experiment at Plataforma Solar de Almería in the 80s. And different phase change media, normally different nitrates or carbonates of salt carbonates, but also some other materials like potassium oxide, hydroxide. Sorry. Regarding the experiences, you can see here different experiences. They are interesting because, in fact, these have been the main experiences before the development of CSP in Spain during the last 3 or 4 years. So these experiments or these experiences have been very significant. For example, we can see that with parabolic trough plants, we have had experiences with oil, with thermal oil as a storage medium with different operating temperatures and different concepts. For example, we can see experiences with thermocline tanks and with 2-tank systems, like these two. We have had also experiences with dual medium tanks, like in the SSPS project in Almería, with oil and cast iron. These dual storage mediums are quite promising. And we have also had experiences at central receiver systems with different mediums like oil, sand, rock, or liquid salt, and also different techniques like dual medium tanks or 2-tank systems. I just want to call your attention about the fact that the most significant experience with molten salts or liquid salts was at the Solar 2 project in Barstow, in California, in the United States, and the thermal capacity of this system was 110 megawatt hours thermal, with a temperature in the cold tank of 275 degrees C and a temperature in the hot tank of 565 degrees C. That means almost 300 degrees difference between the hot and the cold tank. And keep those numbers in mind. We will turn to these figures again. Now I will have a look at the commercial installations, the solar thermal power plants actually currently operating or being constructed in Spain with thermal storage. Two of them, two central receiver systems, PS10 and PS20, use short-term thermal storage using pressurized water tanks, and two of them, or another central receiver systems uses direct direct thermal storage system in molten salts in two tanks. This is Gema Solar near Seville, which is the plant with such a large thermal storage system of 15 equivalent hours, and some plants, not only Andasol one, but many other plants, use these are parabolic trough plants. They use an indirect thermal storage system with two tanks, also using molten salts as heat storage. The most representative, of course, is Andasol 1, because it has been the first plant to consider this concept, and now it's currently operating with this system. This picture, you can see the tanks of the thermal storage system of PS10. They use pressurized water, and there's a sliding pressure mechanism during discharge of the storage system. Of course, the vessels must be pressurized. They are pressure vessels, so they are rather expensive, and they cannot be very big. The main characteristics are described here. The maximum pressure is 40 bar. It's close to the pressure of the steam at the receiver. The thermal capacity is 20 megawatt hours, and that's equivalent to 50 minutes at 50% load of the turbine, and the total volume of the tanks is 600 cubic meters. The system is made of 4 tanks, which are sequentially operated. Here you can see a drawing of one of these systems with steam charging and steam discharging. These systems or this type of thermal storage is not appropriate for a large capacity storage. It's not appropriate for large capacity storage. So other solutions must be considered. The obvious alternative for central receiver, especially for central receiver systems, is to use the same fluid both at the receiver and at the thermal storage system. In this case, molten salt. It could be also liquid sodium, but sodium has some important safety problems, so normally it's not considered for these applications. But with molten salt, this problem doesn't exist. The thermal capacity of the tanks is proportional to the temperature difference between the hot and the cold tank. The design is a 2-tank design, and the molten salts, the molten salt mixture which is used in these systems is a commercial material, which is commonly used in the process industry. So most of the equipment to manage the storage medium, the molten salts, is existing and can be acquired in the market. They operate at atmospheric pressure, so the vessels don't need to be pressure vessels. They have to be, of course, well isolated from the environment to avoid thermal losses. This picture is from Solar 2 at Varstu. This is the 110 megawatt thermal system, and these are conditions of the molten salt with with a delta T between the hot and cold tank of nearly 300 degrees. In this case, a little bit less, but in that range. And the limits for the operation are the maximum temperature must be limited, because above these temperatures, this mixture may experience some decomposition. And of course, there's a need for heat tracing, because in case of a long period without solar radiation, there's a risk for the molten salts to freeze. That should be avoided, because it's very expensive to melt them again, very expensive in terms of energy and very costly also in terms of time and effort, and the equipment is rather expensive. Even so, the total cost per kilowatt hour thermal is interesting, I would say, at least in the Spanish market. That's why many projects include a large storage system in the Spanish market. Well, in this case, this concept has been adopted by the Gema Solar project, and the Gema Solar project is a 17 megawatt plant with 15 hours equivalent capacity. That means roughly 1 gigawatt hour thermal of storage capacity. That's about the same of the storage capacity of the Andasol system, which is described here, and we can see a picture of them, of this system here, these large tanks. As I mentioned, the thermal storage capacity of the Gema Solar plant is roughly the same as the thermal storage capacity of the Andasol thermal storage system, but because the temperature, the delta T between the hot and the cold tank is more than double than that of the Andasol, the volume of salts is approximately 1/3 of that of the Andasol plant. Therefore, the cost per kilowatt hour stored is much less. It's considerably less than that of the Andasol plant. If we consider the Andasol plants, the main difference is that this thermal storage for parabolic trough plants need a heat exchanger, because we must transfer the thermal energy from the solar field to the storage system, and the heat transfer fluid is not the same at the solar field and at the storage system. And on the other hand, the maximum temperature of the thermal oil, of the heat transfer fluid of the solar field, is limited to a little bit less than 400 degrees. Therefore, the maximum delta T that we can achieve in the storage system is about 100 degrees. That's almost 1/3 of the delta T that we can achieve in a central receiver plant like Gema Solar. Therefore, the cost of the heat storage in terms of euros per kilowatt hour is much higher for this type of plant. In any case, these systems provide a high storage capacity to parabolic trough plants, which other way would be difficult or very expensive to achieve, for example, with using thermal oil as storage medium. There's a need for heat exchangers, of course, which increases the price of the installation, and because of this limited delta T, we have large volumes of molten salt and higher investment costs. Here we can see some of the characteristics of the undersalt storage, which, as I commented, will be replied in many projects, at least probably nearly 20 projects in Spain. You can see that's a 2-tank molten salt storage with a nitrate salt mixture, melting point of 223 degrees C and a storage capacity of roughly 1 gigawatt-hour thermal, what in the case of a 50 megawatt plant is equivalent to 7.5 hours at full load operation. The storage tank size is 14 meters in height and 37 meters in diameter, and there are more than 27 tons molten salts in the system. Flow rate is the maximum flow rate is almost 1,000 kilograms per second, and as we can see here, the delta T between the cold tank and the hot tank is a little bit less than 100 degrees. The hot tank temperature is limited by the temperature of the heat transfer fluid of the solar field, and the cold tank temperature is limited by the melting point or the freezing point of the molten salt mixture. Again, here we can see here the picture of this thermal storage at the Andasol plant. There are also some advanced experiences or concepts which are being explored. For example, for Trough plants, the concept of storage in reinforced concrete with embedded heat exchangers is being explored mainly by DLR together with other German companies. There have been some pilot installations at Plataforma Solar de Almería, and the expected investment cost will be in the range of the 20 euro per kilowatt hour. A rough idea about the cost of the molten salt storage for Powerwork Trough plant is that it can be in the range of 25 euros per kilowatt hours, all equipment and molten salts included. For central receiver systems with direct thermal storage, the cost will be significantly less. Other concepts are thermocline tank storage, which could reduce also the cost of the installations, also for parabolic Trough plants. For direct steam generation plant, it's necessary to develop phase change materials storage because of pinch point issues, and well, these types of storage are being explored also at pilot installations at PSA, at Plataforma Solar de Almería. And for volumetric receiver plants, sand storage or even ceramic pieces storage concepts are being developed. These types of storage use sand or ceramic pieces or even metallic different metals to store the energy, and of course the energy can be, well, the system is charged, making the hot air from the volumetric receiver flow through the thermal storage and in one direction, and it's recovered or discharged, making the cold air flow in the opposite direction. This is roughly the way these systems will work. Summarizing a little bit, thermal storage systems are thermal energy storage systems. Present many benefits for CSP plants, for solar thermal power plants. The first or the most important are that this thermal storage improves the plant controllability and operability, and expand the range of possible operating strategies. Facilitates the dispatchability. This is, as we have commented, very important for utility markets. And if they are adequately designed, can improve the efficiency of the plant and the profitability of the project. Normally, when we operate from the thermal storage, the efficiency of the turbine, of the power cycle, decreases a little bit, because normally the operation is at reduced conditions, at less temperature than if we operate directly from the heat transfer fluid. But this loss of efficiency is normally compensated by the fact that the plant can operate during more time at high load, and there are less starts and stops of the plant. In this sense, because it reduces the number of start-stop cycles, the use of a thermal storage system normally extends the lifetime of equipment. On the cost side, of course, a thermal storage increases the investment, because we need not only the thermal energy system, but the solar field has to be also oversized to take advantage of this thermal energy system. For example, for a parabolic trough plant, a 50 megawatt parabolic trough plant, normally the size of the solar field is about double of the size that would be needed to operate the turbine at full load at the design point. It's a bit complicated, but roughly we have almost double size solar field with a 7.5 hour thermal storage system. And on the other hand, the operation maintenance cost may be increased a little bit also by the fact of the operation of the thermal energy storage system. Well, this is about thermal storage. Hybridization is the other point of these presentations. Hybridization consists basically in using two energy sources, solar energy and fossil or renewable fuel. And of course, if we have these two energy sources, we can take advantage, for example, of the fuel to operate during transients, or to start up the turbine, and start to warming up the turbine before the sun rises, to reduce the number of turbine stops, or to increase the full load operation time. And hybridization can be even used to maintain the temperature of the heat transfer fluid or the storage medium. In fact, for example, in Spain, this is the legal use of natural gas in solar thermal power plants. There are different hybridization options. I like this brief summary presented by Solar Paces. We have three main options for hybridization. The options today are hybridization, where the solar energy goes into steam cycles. The most direct and common of them is to integrate solar energy and the energy coming from the backup fuel in a steam turbine. But we have also the option to integrate the solar energy in a combined cycle. Even normally the solar energy is integrated into the heat recovery boiler of the combined cycle. These are the options today, but from the point of view of the best use of the quality of solar energy, it's very interesting, the concept to integrate the solar energy into the gas turbine part of the combined cycle. This concept is being explored in different projects. Perhaps the most significant is the REFOS project, developed by DLR at Plataforma Solar de Almería with a closed volumetric receiver. Here, the solar energy from the volumetric receiver is integrated into the gas turbine part, taking advantage of the high exergy of the solar radiation. These are the main three concepts. I will describe with a little bit more detail the two concepts or the two options that are being used today. The first one is just to integrate backup fossil or renewable backup system into a solar power plant. In this diagram, well, it's not for the 30 megawatt solar electric generating systems. It's general for any type of steam turbine system or Rankine cycle. We can integrate the backup fuel in different ways. We could include a boiler, an auxiliary or secondary boiler, which can be used to generate steam when there is no solar energy input or it's insufficient. Therefore, we can have the boiler or the fossil, the gas. Normally, it's natural gas, the natural gas boiler on the steam side, or we can have it. In fact, it would be a heater on the heat transfer fluid side, on the oil side. In this case, for most of for today's parabolic trough plants. Any of these options have certain advantages and disadvantages. In the SEX plants, you have the CERT in California. Some of them, they have used this configuration with the boiler on the steam side. In other plants, the boiler or the heater has been placed on the oil side. In the case of parabolic trough plants with thermal oil as heat transfer fluid and thermal storage, like many of the plants in Spain, for example, the Andasol plant, the auxiliary boiler is placed on the oil side. This is due to different reasons. First of all, is that according to the Spanish regulation, the natural gas burner must be placed on the side of the heat transfer fluid. The second, other reasons are that this auxiliary burner can be used to heat up the oil when it's necessary and directly heat up the molten salts to avoid freezing. So it has different functions. Well, in this case, as I said, in Spain, the heater, the natural gas heater, is placed on the oil side. Finally, the combined cycles, the integrated solar combined cycle systems, which are being developed in North Africa, follow the second scheme I presented. The solar energy coming from the solar field is integrated in the heat recovery boiler of the combined cycle. And there are also different options to make this integration, but basically this is this is the scheme. With this type of configuration, the solar field size is limited, and the solar fraction, that is the amount of energy, of electricity generated from solar energy divided by the total electricity generated by the plant, is rather low, in the range of 10 to 15%, maybe 20% at most, because because other way the relative size of the steam turbine and the gas turbines should have to be modified, and the operation in absence of solar energy would be less efficient. So there are limits for an efficient operation of these types of plants for the solar contribution. In any case, it's a very promising concept. It's a very interesting concept. It's interesting because of different reasons. It saves conventional fuel, natural gas normally, and on the other hand, it gives an opportunity to develop the solar technology at a reasonable cost and with very limited risks. That's why this was the concept supported by the World Bank for different projects in different countries, in North Africa, in Mexico, in India, and so on. Well, just to summarize this about hybridization. Hybridization improves controllability and operability of the plant, facilitates dispatchability, like thermal energy storage, improves in all cases if there are not design errors, the overall plant efficiency, improves the capacity factor of the plant. That's the equivalent number of equivalent hours that the plant is operating during the year, and the profitability of the plant. Of course, that depends on the price of the fuel, but at the moment, it's well, for natural gas, for example, in Spain, it's profitable to use hybridization and extends equipment lifetime. As you can see, these benefits are very similar to those provided by thermal energy storage. A combination of thermal energy storage and hybridization, like we have seen in the Andasol plants, is very interesting because it provides a lot of flexibility to the plant, many different operation strategies, options, and with the good use of these options, the efficiency of the plant or the generation can be improved. Of course, hybridization has also as a counterpart that increases the investment and operation and maintenance cost, and these operation costs depend on the price of the fuel. And another disadvantage, this is conceptually more important, is that these plants have CO2 emissions. The amount of CO2 emissions depend of course, on the use of the natural gas. If natural gas is the fuel, if the fuel was derived from biomass, this would be less important, and and depend on the fraction of hybridization. For hybridization in steam plants, normally the fraction of fossil fuel is between 15 and 25%. For hybridization following the integrated solar combined cycle systems, the fraction of of natural gas generation from natural gas is between 80 and 90% normally. Well, and this is all. Thank you for your attention. I hope that this conference or this seminar has been interesting for you.
Okay, thank you very much. Thank you very much, Manuel. So we are going to some questions now. You can then submit your questions for the session today. So let us put into place the new configuration of the screens, and let's proceed with the questions. So there is a first one. Yes, about the typical percentage losses with thermal storage, which medium has the lowest losses. Thank you.
Sorry, I didn't. What are the typical percentage losses with thermal storage?
Yes, you can read it. You can read the question in the Q&A window, which is close to the attendee list. But yes. The point basically is, well, what from 100, let's say from 100 megawatt hours from the thermal fluid going into thermal storage, how much can I recover?
Excuse me, I have some echo. Well, now it's okay. That depends, of course, of the type of storage, or on the temperatures, on the isolation of the storage tanks in this case. But normally the thermal losses of the tanks are rather low, are very low. Normally, if you use the molten salt or the thermal energy stored during the same day or during the following day, the losses are less than 1%. And that can be measured also in terms of temperature decrease of the hot tank, which may be in the range of 1 or 2 degrees C per day. But the efficiency when generating from the storage tanks decreases, because the temperature of the steam generated is normally a little bit lower. Then depend on the characteristics of the power cycle, but normally you have a reduced efficiency. For example, it's just these figures are maybe not very precise, but but they may be approximate. When generating directly from the field, from the heat transfer fluid, from the thermal oil, the rated power of the turbine is 50 megawatt, and you normally generate at 50 megawatt power if there is enough energy coming from the solar field. If you generate from the thermal storage system, this power decreases to 45 megawatts or 46, in that range, because the temperature is lower and maybe the pressure too. So, well, I hope that answers. To be more specific, I would need to go to a concrete case, but I think that gives an orientation. In any case, thermal storage systems are quite efficient. The main problem, or at least molten salt thermal storage system, the main problems have to do with the cost and with the need to avoid, by any means, the freezing of the molten salts.
Okay, thank you very much. So we have two related questions to the point that you indicate here. The cost of storage, I suppose, without including the oversized of the solar field, but just the cost. For instance, if we take Andasol, what would be the associated costs to cost of tanks, molten salts, and heat exchangers? And also another question related to the point that you mentioned, if the salts freezes at 220, then all the piping must be kept at this temperature.
Yes.
So how do you handle it? It's a permanent tracing of the pipes, or how is it managed? So thank you for these 2 points.
Yes, the answer to the second question is very clear. Yes, the molten salts must be always kept liquid. If you permit them to freeze, then the cost to melt them again, and the cost in terms of operation and maintenance time, and maybe the need for repair of equipment, and the cost in terms of energy to melt them again is very high. So molten salts must be kept liquid at all time. That's normally made by means of heat tracing, conventional heat tracing of pipes and even tanks, and also can be done by means of by using the heater, the natural gas heater, for example, in the Andasol type plants. You can heat up the oil and then use the oil to increase the temperature of the molten salts. So it's possible to keep them liquid at all time, but it's very important to do it so. The first one is more difficult to answer. The approximate cost per kilowatt, that's per power. I mentioned that the cost per kilowatt hour, that's per unit of energy, is in the range of 25 cents per kilowatt hour, maybe 20, maybe 30, but in that range. And it's not linear. It's not linear with the size of the storage system, because depends on, of course, on the amount of salts, but it depends also on the equipment. So it's not linear at all. But for a 50 megawatt plant with 8 hours storage, maybe in that range. And in terms of cost per kilowatt, just to give an idea, a 50 megawatt plant without thermal storage and with roughly in Spain, I'm always talking about Spain because I don't know figures for any other country, but that may be indicative at least. A 50 megawatt plant without thermal storage, maybe, for example, or maybe about 200 million euros with a solar field of 300,000 square meters of mirrors. Okay, that's it's a rough number. Maybe 180, maybe 210, but in that range. And if you include 7.5 hours storage, and that's whole type, as I call it, 7.5 hours storage in two tanks with molten salts, the cost of this plant may be at least 50% more. So that can give an idea, but well, it's not precise because it's not. These figures are not linear at all. So that these are the figures for a 50 megawatt plant with and without thermal storage, and the one with thermal storage with 7.5 hours. The solar field size would go to 500 or 550,000 square meters of mirrors. That's about 1.8 times the mirror area required for the plant without thermal energy storage.
Okay, thank you for the information. Another question about the thermochemical storage. Can you illustrate on this? Is there any experience on that?
There have been several experiences. Well, thermochemical storage is based mainly in the realization of a chemical reaction, of a reversible chemical reaction, which is endothermic in one direction and endothermal in one direction and exothermal in the opposite direction. Another related with this is also the production of solar fuels, for example, through solar reforming of methane to produce hydrogen. But the general principle is that is a chemical reaction, a reversible chemical reaction, which is endothermic in one direction. This is the charge direction. It takes the enthalpy from the solar energy, or the heat from the solar energy, and it's exothermic in the opposite direction. So you can use it in this direction, in this opposite direction, to I would say discharge the storage, or to use the stored energy as thermochemical energy.
Okay, thank you. So now a question about hybridization with biomass. What's your opinion on this? According to Rodolfo Gomez, biomass would completely eliminate the need for heat storage. Biomass would be stored instead of heat, avoiding the high costs of molten salt storage. Well, following this question, I have to remember that Spanish regulation allows for hybridization with biomass. However, there is no one single megawatt in my knowledge hybridized with biomass among the 2,400 announced megawatts. So I guess that the flexibility of biomass profitability has something to do. Can you illustrate a little bit more on this? Thank you.
I agree with Rodolfo. The use of biomass combined with CSP, that's hybrid biomass solar plants, is really interesting and promising. Those plants should be 100% renewable and would be or could be dispatchable, etc. So it's really interesting, but of course there are some problems. You are right. There's the use of biomass in Spanish regulation is permitted up to 15%, up to 50%. Sorry, in CSP plants, but there's no one single megawatt in foreseen for the next year. The reason is that it's there are some problems regarding